Good evening, everyone. Myself Gautam Sharma. I welcome you all in a Sapience Education. So today I am going to discuss about the electric charges and field topics. This is the part 2 video, and part 1 video I have already recorded. So this is totally theoretical lesson. So first of all, I would like to discuss about what is electric field lines. Electric field, the region surrounding a charge in which its electric effect can be felt is called electric field in a given region. Let us take a charge Q, which is positive, and let us try to keep an electron which is negative. So what will happen? There will be a attraction between them. Attraction between them. It means that this region has a electric field which has been created by the charge plus Q. Now let us suppose you keep this electron at this at infinity. So what will happen? There will be no changes. Neither attraction nor repulsion. It means that there is no field at all. So what happens? Electric fields are the surrounding where any external charges experiences a force. Whenever you put in this field, let us consider this is the field. When you put the field, definitely there will be a force. There will be a force. What type of force? Either repulsion or attraction depends upon the polarity. So the force experiences by charges on its surrounding. So I hope you have understood electric field. Okay. Now let us go for next topic. What is electric field intensity? Electric field intensity due to point charges. See, it is defined as the force experienced by a unit positive charge passed at that point is known as electric field intensity. See, let us assume that there is a charge Q. Okay, there is a charge Q. It may be positive or negative. If I will keep here a charge Q, charge plus Q, which has one coulomb of charge or unit positive charge. Unit positive charge. So it will experiences a force, right? It will experiences a force. Got it? So this force is known as intensity. Intensity at this point. Now, if I will put this charge here, so the force will increase. It means that intensity has been increased, right? It means that intensity changes when you changes the position of the charges with respect to this charge. I hope you have understood this. Now see here, we can directly write the formula for the electric field intensity, that is E is equal to force experienced by unit positive charge where charge tends to 0. Limit charge tends to 0. Now, as per the Coulomb's law, what we have learned, Coulomb's law, F is equal to Q1 Q2 by R square. This is a Coulomb's law. Now, see here, it is your positive charge Q, and there is another charge. If there is a charge Q and there is one unit charge, that is 1 Coulomb, and the distance between this is R. So, what will be the force experience? Force experience is equal to Q1. Q1 will be Q, and Q2, this is Q2. Q2 is equal to 1 Coulomb divided by R square. So R is the distance between them. So this will be R square, right? And you should multiply it by K. F is equal to K Q1 Q2 by R square. So this is what we are getting an electric field. I hope you have understood now. If you haven't understood, I can again explain you again. See here. See, let us consider this is a charge Q. Okay. And I want to find an electric field intensity at a point P. Electric field intensity at a point P, right? At a point P due to this charge. So I have to put a unit charge Q naught, which is equal to 1 Coulomb, or any unit charge we have to put. Now, as per the Coulomb's law, as per the Coulomb's law, what we will have a force. So force is equal to K Q1 Q2 by R square. Now we have to put this force here. If we will put this force here, so what we will get? See here, we will get K Q1 is equal to Q2 is equal to Q naught, that is unit charge, divided by R square. But we have to multiply it by Q naught. Why? Because electric field is equal to force by Q naught. So Q naught got cancel out. So finally we are getting force equal to KQ by R square. And the direction will be in this direction, electric force direction, right? So I hope you have understood this, right? Now, see here, the electric field is radially outward from the positive charge and radially inward from a negative charge. So let us suppose this is a positive charge. So what will happen? The direction of electric field is in this direction, outward. But let us suppose that if you have a charge negative, so the direction of electric field will be in this direction, inward. So this is known as inward direction. This is known as inward direction. Got it? So this is an outward direction and this is inward direction. I hope you have understood now. Okay. Now what is the SI unit? So SI unit, so this is force by charge, so Newton per Coulomb, volt per meter. So dimension will be mLt minus 3 A inverse. I hope you have understood now. Okay. Now let us go for next topic. Now electric field intensity due to system of charges. See here. You know that due to one charge, we have already derived electric field intensity as equal to K Q Y R square. But now the practical case happens where we want to find electric field intensity at a point P due to several charges, right? Several charges, 1, 2, 3, 4, right? So if we want several charges, for example, there is a charge Q1, there is a charge Q2, there is a charge Q3, and I want to find the electric field intensity at a point P. So let us consider point P. Electric field due to charge Q1. Electric field due to charge Q1 will be, let us consider, electric field is in this direction, that is E1. Electric field due to charge Q2 will be in this direction, that is E2. Electric field charge due to Q3 will be in E3. Now how you will find total charge at this point? So we have to add vectorially. So vectorially we can say that by the principle of a superposition, net electric field will be equal to E is equal to E1 plus E2 plus dot 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 in. Now if I will break this, so you will get E is equal to, first of all, K Q1 by R is R1 square, because its distance we can consider R1, its distance consider we can R2, and this distance is R3, into R1 cap plus K Q2 by R2 whole square into R2 cap dot 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 K into Qn by Rn into R cap. So when you add this, so we can sum up this. I think you have already done lots of things in a class 11. So for net electric field will be equal to K into summation of I start from 1 to n charge Q by R square. So this is the net electric field due to the discrete charges, right? So charge is in the form of packet like this Q1, Q2, Q3. Then you will get this. I hope you have understood this. Now, if suppose the charge is continuous charge, so what you will do? Continuous charge means what? There will be a charge, there will be a different charge. So we cannot take multiple charge and add vectorial. It is very difficult for us. So what we will do? We will do integration. So net electric field is equal to K. We'll see. We will use the same formula, but in place of a charge Q, we have to put dq and we have to integrate it, because if you take dq charge, uh, if we take dq charge, and due to this charge, if the electric field is dE, dE, then total electric field will be what? This, see, let us consider dE. So dE, small electric field due to small charge will be equal to how much you can write? So we can write here K into dq by r square into r cap. Now I want total electric field. So integrate this. So if I will integrate this, so overall electric field will be equal to K will remain constant by integration of dq by r square into r cap. So this is what formula for the continuous charge distribution. I hope you have understood this, right? Now let us go for next one. Next is what is electric field lines of the line of force. So let us see here. An electric field lines is a curve drawn in such a way that the tangent to it at each point is a direction of the net electric field at that point. See here. At this point, I want an electric field. What is the intensity of the electric field? So we have to draw the tangent at this point. If I want electric field at this point, let us suppose this is R. So we have to take a tangent at this direction, either in this direction or this direction. Okay. And the magnitude of the electric field is represented by the density of the field lines. What do you mean by this? See here. If electric field is strong, means what? The electric field lines are separated like this. Okay. So this is a strong electric field. Now, if I want to show the weak electric field, so how you will find? See here, weak electric field. So if I want weak electric field, so we have to increase the gap. See here, this is the gap, this is the gap, this is the gap. So this is a weak electric field lines. Okay, a weak electric field. Here it shows that there is a weak electric field. So whenever you saw a dense number of lines of electric field, so it means that it is the strong electric field region. But when you saw the rare electric field lines, so it means that it is a weak electric field, right? So I hope you have understood now. So an electric field lines is a curve drawn in such a way that tangent to it at each point is in the direction of the net electric field at that point. The magnitude of electric field is represented by the density of the field. Okay. So electric field lines may be like this, may be like this. Okay, depend upon the situation. So let us go for this. Now, properties of the electric field lines. So what are the properties of the electric field lines? See, first of all, it is your imaginary and continuous curves, right? Electric field lines. For example, this is a charge, right? This is charge. So what will happen? There will be an electric field lines in this direction. So this is continuous curve. So we don't know where it is going to end. It may be at infinity. So it is a continuous curve. Curve means don't think like this only. Curve means curve. Straight line is also a part of the curve only, right? Now, from the second property is that it starts from positive charge and end at a negative charge. See here. See, this is positive charge. So it starts from positive. See, it starts from positive. It is going outward and it ends from negative. So it is coming inward. Now let us suppose if you have a positive charge as well as negative charge. So what you will do? So you have to make a curve. See here, let us consider this positive charge. So positive charge, the electric field lines is going in this direction from positive to negative, right? Okay. Right. Now see here, this is your electric field lines, but it is making a curve. Why curve? Because see here, the intensity at this nearby is very high. So what will happen? There will be dense curve. But as soon as you go outward, so the intensity of the electric field is less. So what happened? There will be a more gap. So the more gap is required, right? So see here, there is a more gap. But near the charge, you have a less gap. less gap like this. Okay. Now, third most important form is that it is does not form continuous closed loop. It is does not form a continuous closed loop. So it won't be like this and again like this. See here, half part you are getting. Not continuous closed as this. This is positive. This is negative. So the line you are getting like this, and you are getting line like this. So it is not forming closed loop. This is suppose closed loop, but it won't form, right? So this is what third point is. Now, the always normal to the surface of the conductor. What do you mean by this? Electric field lines is always perpendicular normal to the surface of the conductor. Let us consider this is the surface of the conductor, right? So what is the direction of an electric field line? So the electric field line will be perpendicular to this at this direction. If I draw, another, see here, another like this. So the electric field line at this point will be in this direction. If I want to see the electric field lines, so electric field lines will be in this direction because it is perpendicular to the surface. If I will talk about this one, so this will be in this direction. If I will talk about this one, so this will be in this direction. So always remember that electric field lines is perpendicular, normal to the surface. Normal, always there is a normal to the surface. Normal to surface. I hope you have understood this. Now the fifth point is that can never cross each other. See, electric field, you won't find electric field lines like this, electric field lines like this. Why this does not happen? See here. Electric field lines force never intersect each other because at that point of intersection, two tangents can be drawn and the two lines of the force. And this means that the two direction of electric field at that point, which is not possible. See, if if I am talking about this point and they are crossing each other. Now, if I will talk about the tangent, so how you will find a tangent? So let us draw the tangent, right? So if I will draw the tangent at this surface, so this is the tangent at this surface. And if I will draw the other tangent, see here, if I will draw the another tangent at this surface, so there is another tangent at this surface. So at the same point, we are getting two direction of electricity, which is not possible. You can say that there is in this direction also there is an electric field direction. This is also electric field direction. So it is not possible. Not possible. Right? So I hope you have understood fifth point. Now, very important is that dipole in a uniform electric field. Dipole means what? Two poles. See, very important. Always remember, dipole means two pole. We are talking about dipole. Dipole means two poles. That is, one constitute a positive and another must constitute negative. If positive is 2 Coulomb plus 2 Coulomb, then negative must be minus 2 Coulomb so that it will form a dipole. Right? So in dipole, when we place a dipole in an electric field, so what will happen? It's very simple. What happens? See here. Here we have placed a dipole. See, pl- placed a dipole that is minus q and plus q, which is separated by a 2a, and this is the center, right? Now tell me, if this is positive charge, so the force will act on this charge will be in this direction. See, electric field direction is forming by the blue color. Blue color shows you the electric field lines. So what will happen to the force? Tell me, in which direction force will be applicable to the positive charge? Now let us take an example. You always try to apply your own logic to understand this. Let us consider this is positive charge. So the electric field lines will come in this direction in the positive charge, yes or no? Now if I will put a If I will put a positive charge here only, so what will happen? Repulsion will be happen. And if repulsion will happen, so this what will happen? The force will always act in the direction along the electric field, right? When the charge is positive. Now, if I am talking about the same thing, this is field line, but I am putting here negative charge. So what will happen? It will get attracted. So the force will act opposite to the direction of the field. So from here you can understand the conclusion that what we are talking about. Okay, so here why I have given a force in this direction, force is in positive direction, F is equal to QE, and there is another force which is F is equal to QE in this direction because there is a negative charge. So due to negative, when negative charge is placed on the electric field, so the force will act in just opposite to the electric field. But when positive direction, positive charge is there, so the force will act along the direction of electric field. Now see here, when we add on, so total force will be what? See here, magnitude of the charge will be remain same because it is dipole. So dipole, what happened? Dipole consists of equal and opposite charge. Dipole consists of equal and opposite charge, equal and opposite charge, right? So here when we use to find up electron force, so what will happen? Magnitude of the force will be equal but in opposite direction. See, let us consider this is force 1 having a magnitude of plus 2 Newton in this direction, so there will be another force which will be minus 2 Newton. So net force will always remain 0. So net force will remain 0 when it is placed. Now what will happen? You remember the torque theory? Torque theory, what happens? In torque, what happens? Let us suppose you are applying a force in this direction and another force is in this direction. So let us take another ruler and you are applying a equal force 10 Newton from upward and 10 Newton from downward. So what will happen? Net force will be 0. Net force will be 0. If I will place this 10 Newton in this direction and if this 10 Newton in this direction, then also net force is 0. Net force is 0. Why? Because both are equal in opposite direction. But what are the changes happen when you try to separate? So what will happen? It will create a torque. It will try to rotate it. You have seen the cycle example. So if you are applying a force in this direction, applying force in this direction, so it will try to rotate this, right? So whenever there is a rotation, so it means that there is a torque creation. So there will be a torque. So torque, we know that torque is equal to force into perpendicular distance between the line of action of the force. This is, you should always go through the basic things. I have already taught these things in a class 11. So what happens here? What happens here? See here, this is the perpendicular distance between the line of action of force. So this is the line of action of force and this is the line of action of force. So this is the perpendicular distance. So when you see here, this is your perpendicular distance. Now if the angle is suppose theta, if I will talk about this theta, so if angle is theta, so can you find the distance d? So d sine theta is equal to perpendicular by hypotenuse, that is d by 2a. So from here d is equal to 2a sine theta. Now you can put here in place of d, we can put here d, in place of d we can put here 2a sine theta. So force, what is the value of force? So force is equal to QE. Okay, why? Because electric field is equal to force by charge. So force will be equal to Q into E. So in place of force we have put here QE. Now if we rearrange this, so what we are getting here, 2A into QE into sine theta. Now what is 2A into Q? What is 2A into Q? Dipole moment. Let us see here. What is 2A Q? dipole moment. See here, dipole moment 2 into A into Q is dipole moment P. That is your dipole moment. Okay. So now in place of 2AQ, we can put here P, that is dipole moment in electric field E into sine theta. Now we know that A cross B is equal to AB sine theta. Here also we have got the similar thing. So finally torque is equal to P into P cross E, where P is the dipole moment of the charge. P is dipole moment of charge, equal, right? So I hope you have understood this, right? Now tell me, when P is along E, theta is equal to 0. P is along thing in what? See here, this is the direction of electric field lines, and the dipole moment, I am putting here dipole moment positive Q and negative Q. So from positive to negative, so it is along this. So the angle between this, see earlier it was like this, but now it has become like this. So it means theta is equal to 0. If theta is equal to 0, so torque will be 0. Got it? Because we have already done P is sin theta, torque is equal to P is sin theta. So theta is equal to 0 means what? See, theta is equal to 0 means what? P into E into sin 0. So sin 0, this will is 0. So the dipole is in stable equilibrium. So here we can say that dipole is in stable equilibrium. Now we will go for a case 2. When P is in opposite to A. So when the dipole is in opposite, so what is the diagram for this? See here, you have to do these things by your own. So I am thinking that you should do, because everything you should not go for just spoon feeding. So let us see here, put here minus q charge and plus q charge. So what will happen? So direction of the dipole moment is in this direction. So what will be the what will happen? So electric field, this is electric field direction. So the theta is equal to g 180. So tau is equal to also 0 in this direction. So if dipole is in unstable equilibrium, now, if E is non-uniform, the dipole will experience both resultant force and a torque. So, its motion will be combined translatory as well as rotatory. See, if electric field is non-uniform, so what will happen? It will create a torque as well as it will also create a translatory motion. Why translatory motion? See here, we have already seen here, if force will be like 10 Newton in this direction, and here it is 11 Newton. So what will happen? It will, this whole dipole will try to move in this direction, because net force is acting 1 Newton in this direction. So this is very key factor. Okay. So I hope you have understood this. So till now, thank you for attending the class. So I will explain next thing in another class. Thank you.